Good morning, esteemed colleagues and guests. I am Jianing Luo, and I'm delighted to be here at SIGraDi Conference 2023 to present our work titled Deep Generative Modeling Tasks, Automatic Generation of Building Facades with Pix2Pix GAN for Hong Kong City Expansion and Renovation. This research explores new dimensions in providing architects with design scheme references and theoretical support for the later research on automatic design generation. The integration of new buildings with historical urban districts is crucial, as cities' historical buildings embody their memory and unique identity. Architects are encouraged to consider existing architectural styles when constructing new buildings or renovating old ones, ensuring the preservation of historical lineage while modernizing the city. The facade, a vital element of architecture, plays a key role in this process, requiring careful consideration of its aesthetics and functionality. Traditionally, categorizing and redesigning facades was labor-intensive and subjective, but the emergence of automated building design offers a more objective approach. Innovations in automated architecture, such as generative adversarial networks and their variants like conditional GANs, have significantly impacted architectural design. These technologies enable the generation of designs that align with specific datasets, making it possible to replicate and adapt styles across different urban areas. Pix2Pix, a GAN-based algorithm, has been particularly influential in synthesizing images and facilitating the transfer of urban and architectural styles. It learns to transform input images, like bitmap images, into corresponding output images, offering a new, efficient approach to urban design and facade generation. This research used an automated design approach with Pix2Pix GAN, which can provide informative design strategies in the pre-planning phase of urban renewal. The testing procedure drew upon the large amount of collected data and completed semantic segmentation of bitmap, which facilitates the seamless integration of both functional components and the distinctive architectural style encapsulated within the architect's predefined building facade. In this section, the research described the deep learning models used in this experiment, the data sources, the methods used to generate the training dataset and test the trained models, and the training and testing process. Specifically, that is elemental segmentation of the existing building facade from the input, corresponding to the semantic segmentation of the bitmap guidebook, encoder UNet, generator with discriminator, known as the patch GAN. From the input to the generation of output is shown below. Based on the data-driven generative approach and the properties of convolutional neural networks, this research employs a deep learning network, such as Pix2Pix, and use GANs as the main algorithm for performing the image-to-image translation task. At the same time, a deep convolutional neural network is trained to provide a sufficient database for the process. UNet is a type of convolutional neural network that allows for more accurate segmentation of images. And the discriminator in this network architecture is a convolutional patch GAN classifier, which only penalizes structure at the scale of local image patches. According to the research objectives, urban block facade data that meet the requirements are collected and processed, and the data are organized, classified, and labeled. We chose the old neighborhoods within the city limits of Hong Kong as the scope of analysis. According to Figure 2, the initial data of building facade were acquired, and a database was created using multiple sources such as Google Map and photo albums, and the building label images were manually drawn according to the guidebook requirements and corresponding colors in Figure 3. After creating a database of building facade images, the photographs in it need to be corrected for perspective, and to ensure that the horizontal and vertical elements in the building facades presented in the photographs are as horizontal or vertical as possible to the edges of the photographs. In the data processing step, the original facade images are simplified in the form of color annotations. The color categories in the manually drawn bitmap include background, facade areas, windows, decorative divisions, store signs and graffiti, doors, fences, and awnings in Figure 4. These labels can represent most of the elements in the building facade. In this step, the size of the processed real building facade image and the building label image are both 256 x 256, respectively. One of the challenges when creating machine learning models is the extremely large amount of data required for unsupervised training. More specifically, it is time-consuming to generate many vector building label images for each data set. In this research, 128 images were selected out of 160 data, of which 96 were used as the training set and the remaining 32 as the test set. The Caesar of each original image after processing is 256 x 512, which contains two 256 x 256 images. Thus, it is necessary to separate the real building facade image from the building labeling image first and define the function that loads the image file and outputs the two image tensors to draw samples of the input image, building labeling image, and the real photo of the building facade image, known as reality and bitmap. In the pre-processing stage, we apply random dithering and mirroring to pre-process the training set. That is data augmentation in figure 5a. First, each 256 x 256 image is resized to a larger height and width of 286 x 286. Then it is randomly cropped back to 256 times 256 and randomly mirrored from left to right. Finally, the images are normalized to a range of 1 to 1, known as data normalization. In testing the function, first the image is passed from the test set to the generator. Then the generator converts the input image to the output, and finally the prediction is plotted. The test results are shown in figure 5b. In this experiment, we use the existing building facade information to automatically generate new building facades with the same style and then compare the similarity and difference of the generated images with the existing building facade pictures to validate the generation effect of this deep learning model and method. Furthermore, the final model attempts to transplant the historical and cultural styles on building facades in old urban areas to undeveloped community projects. In the analysis of facades, two distinct styles are identified in Hong Kong: the high-density dwelling facades and the veranda-style architecture with street-level stores. The generated facades using new technologies demonstrate orderly separation of windows, floors, and columns, with a variety of window sizes and a more complex veranda design that includes distinct street-level features. These new facades maintain the perspective and integrity of the existing structures, offering a continuous appearance where previously there were separations due to construction phases or the passage of time. Materials like glass and metal in the existing facades, which show reflection and refraction, are less evident in the generated facades, with reflections being minimal. The design aesthetic is improved in the generated facades by varying repetitive elements like doors and windows, thereby enhancing richness and uniformity. The generated facades also offer a refreshed appearance by extending original textures and colors, providing a diverse palette and additional options for architects and urban designers, especially for older buildings that have accrued stains and tend to monochromaticity. Deep learning has enabled machines to learn and replicate building facade styles across large areas, summarizing the intricate relationships among various facade elements such as walls, windows, balconies, and signage. The Pix2Pix GAN model can assist architects and urban designers by quickly generating stylized facades, reducing the subjectivity and randomness of experience-based design. Additionally, by analyzing outcomes from deep learning models, designers can discern underlying patterns in facade data, which can inform facade design in undeveloped urban areas and contribute to larger-scale urban design projects. This research developed a Pix2Pix GAN-based conditional generative adversarial network to preserve the architectural style of historic districts during urban renewal. It has shown that deep learning is capable of effectively capturing the essence of building facade elements and their design structures by abstracting and reinterpreting various components, like columns and balconies, into a GAN-based facade generation model, particularly in the dense urban old district of Hong Kong. Furthermore, the data-driven generative methods and the capabilities of convolutional neural networks offer new prospects for computational design in architecture. These GAN-based tools enable architects and urban designers to minimize their subjective biases, expand their design perspectives, and provide practical design previews for urban blocks, while also allowing for the summarization of design rules for application in larger architectural and urban planning projects. Thank you for your listening.